All right, moving right along here. Chemistry 3202, course overview, review. All right, this is Unit 2, Section 3, Lesson 4. This is another important lesson, I guess, on titration curves. Definitely going to have something on the public exam here with this, no doubt about it. So let's have a look at titration curves. Dealt with page 608 of your textbook, and there's a couple questions there as well that you can give a try. And don't forget, all kinds of stuff online and lots of public exams that you can get at and look at what types of questions are coming up here. Okay, here's the outcomes for this. We need to be able to draw and interpret 3 different types of titration curves. So we're going to look at each type of these curves, how to identify which is which, and be able to draw it yourself, of course. Okay, and here we go. Okay, the very first thing we're going to look at is the titration of a strong acid with a strong base. So let's just set the stage here now. You're going to take some sodium hydroxide and put in a burette, and you're going to start slowly adding it to a sample of hydrochloric acid, 1 milliliter at a time, a half a milliliter at a time. And every time you put a little bit of sodium hydroxide in the sample container with the hydrochloric acid, you're going to measure and record the pH. All right? So what we're going to come up with is a little curve that's called the titration curve, and it's going to look something like this. So as you're slowly adding sodium hydroxide, the titrant, okay, and this is the one that we know it's with a strong base, so this is the one that we know the concentration of. We're slowly going to add this, and we're going to add it and stop, add it and stop, add it and stop. And each time we stop adding, we have a pH meter that's going to record the pH for us, and we're going to generate a graph. So on this axis, we're measuring the volume of sodium hydroxide that's being added. And on the y-axis, we're going to start measuring the pH change. So here we go. Now, if we're going to take a strong acid, something like sodium hydroxide, what's going to happen is the pH curve is going to start very, very low. Okay, and it's going to be down around, say, pH 2-ish, depending on the concentration of the hydrochloric acid. It's going to start really low because the concentration of hydrochloric acid is a strong acid, and it's going to be, really low. So there we go. So it's going to be the initial pH of our sample. So before we add any sodium hydroxide whatsoever, at volume 0, we're going to start off at a very, very low pH. What we notice with the pH curve is we see a real quick little jump up, and then as we continue to start adding sodium hydroxide, the hydrochloric acid is still in excess, isn't it? Because we've got a lot of hydrochloric acid in that sample, and all we're doing is adding a few milliliters at a time of sodium hydroxide. So the concentration is going to be mostly, what's in the bottle is going to still be mostly hydrochloric acid, because as the sodium hydroxide is being added, it's instantly being neutralized. So for that reason, what's in the container essentially is still hydrochloric acid. Some of it is starting to disappear. So the pH is kind of level here, and it just rises ever so gently. It stays really, really level because we're adding sodium hydroxide, we're neutralizing it, so we still have excess hydrochloric acid. Remember the calculations we did on the last lesson? Because we got excess hydrochloric acid, we're still going to have a pH that's going to be pretty much acidic. So we continue to add the sodium hydroxide until eventually what happens is all of a sudden the pH begins to skyrocket up like that. So it stays level, and then all of a sudden, poof, it rockets up like that. And as we continue to add sodium hydroxide, what we notice is that it skyrockets for a period of time, and then all of a sudden it begins to level off once again. Okay, well, what's up with that? Well, what we're seeing here is somewhere around this volume right here, all of the hydrochloric acid has now been neutralized. Every last hydrochloric acid or every last H3O plus has been neutralized. What's happening here now is once all the hydrochloric acid is gone, now all we have in the container is sodium hydroxide. And that's why the pH would level off, because as we continue to add sodium hydroxide, the pH is going to be the pH of the sodium hydroxide. And generally sodium hydroxide, depending on the concentrations, usually up around 11, 12-ish like that. And we're going to see, a pH that's going to level off up there. Okay? So, what can we draw from this graph? And what we see is we have a very important point here which is going to be called the equivalence point. Now remember from our acid-base titration experiment, we said the equivalence point is where we have equivalent amounts of acid and base. It's the point where all of the acid is going to be neutralized and all of the base is neutralized. So everything is neutralized. We're at that equivalence point. And the way we mark the equivalence point is we look at the vertical region and we try and eyeball the vertical region of the graph, and we say that this is somewhere near the midpoint of the vertical region of the graph. And what we say then is, as we draw this across, we would say that this is the pH of equivalence. And in this case, we're saying that because it's a strong acid and a strong base, it's going to be somewhere around 7. All right, only for a strong acid or a strong base. Okay, it's not always 7. It depends on what the strength of the acid is or the strength of the base, and we're going to talk about that now in a minute. Okay, what we also know is that this halfway equivalence point, if we drop a line down, what we can figure out here now is that, hey, this is now the volume at which we've equivalently neutralized the hydrochloric acid. And we used to get that by doing successive trials, doing 3 trials, taking the average. What we can do here now is simply do a titration curve, which we have a pH meter, and we could get this curve, and we would take the midpoint of the vertical region, and we would know what pH this was happening at, and we would now know what volume we would have to neutralize the hydrochloric acid. So we could now take this value, the volume, and do a calculation to do our stoichiometry on. So it's a real nice way of looking at it. Now, one of the important things, I guess, of this graph is that not only does it show us the pH at equivalence, it now gives us an understanding and an idea of what we should use for an indicator. Because remember, we said if we use phenolphthalein, which changes color at 8.2, so below this line it was colorless, but anything above 8.2 is going to be pink. So what we're going to say then is that as we start adding sodium hydroxide to this container, it's going to start changing pink about right there. That's very close to the equivalence point. So close, in fact, that if I drop my line down from where the color changes, it's almost identical to the volume of equivalence. So in doing so, by picking an indicator that changes somewhere in this vertical region, either slightly above it or slightly below it, we can see that we can minimize any error from our visual cue. We're seeing it going from colorless, 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 colorless to pink. We know that when it changes to that light pink, we're very, very close to the equivalence. If I picked an indicator that changed color at, say, pH, I'm just looking at my indicator table here. Suppose I picked Congo red. Congo red changes color from at about pH 3, and it goes from blue to red. So at about pH 3, Congo red, it's going to be blue, 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 and then all of a sudden at about pH 3, it changes to red. Right there. Now, if I take that as my visual cue and drop that volume down, look at the error associated with the volume. My visual cue is that Congo red is going from blue to red at about pH 3. That's way too early. It's not even in the vertical region, let alone close to it. So look at the error when I say, okay, stop, and there we go, that's the volume. So that's no good. So that's why we want to pick an indicator that changes really, really close to the equivalence point. All right, so we want to minimize the error. And I'm just going to leave that on there. All right, that's where phenolphthalein is going to change color. So with a strong acid and a strong base, a characteristic thing that we look for is it's going to start very, very low because we're dealing with a strong acid, and the pH curve is going to end very, very high because we're dealing with a strong base. If this was a weak acid, the curve would start much higher. If this was a weak base, the curve would end much lower. So because we have a strong acid with a strong base, we're going to start really low and we're going to end really high. The pH is going to be somewhere around 7 for 2 strongs. Okay, let's look at another one. Here's the reverse situation. In this case, what I'm going to do now is I'm going to put my sodium hydroxide as my sample, and the hydrochloric acid now, or the strong acid, doesn't necessarily have to be hydrochloric, it could be nitric or something like that, but the strong acid is what's going in the burette. So this time, when we do the graph, again we're going to measure the pH change over time, but this time it's the hydrochloric acid that's in the container, and we're going to add the hydrochloric acid slowly. So this time we're going to start it high, because the only thing that's in the container is going to be the sodium hydroxide. At volume 0, we haven't added any acid yet. The only thing in that bottle is going to be strong base, something like sodium hydroxide. So this curve is going to start really, really, really high. And as we slowly add the hydrochloric acid, the pH is just gently, gently, gently dropping, because, you know, like sodium hydroxide is really strong enough to neutralize every drop of this hydrochloric acid. We've got excess sodium hydroxide in the container. All right, so it's going to stay level for a long period of time because the base is in excess. All of a sudden, when all that base gets neutralized, the pH is going to start to plummet, because the sodium hydroxide now is all used up. There's no more of it left to try and withstand any more of the hydrochloric acid. The hydrochloric acid has been neutralized, neutralized, neutralized. All of a sudden we get to this point where every bit of the sodium hydroxide now has been neutralized. If we add one more drop of hydrochloric acid, the pH is going to plummet, because again we have excess acid. So now the pH is going to be reflective of the acid. And what we notice then is that the pH plummets, and then all of a sudden, very, very quickly, it begins to level off, because the hydrochloric acid now is going to be in excess. So there we go. It levels off because now the acid is in excess. We've got lots and lots and lots and lots of hydrochloric acid added. At this point, all the sodium hydroxide is now gone. So once again, we take our vertical region, the midpoint of the vertical region right there. That's going to be our equivalence point. All right, the pH where we have equivalent amounts of acid and base. We measure it back. The pH in this case, because it's a strong with a strong, it's going to be somewhere near 7, but not always 7. It might be like 7.1, 7.2. This depends really on the strength of the acid and the strength of the base. It depends what you're mixing together. All right, there we go. Again, we can figure out the volume of the hydrochloric acid at equivalence. There we go. And what else do we know here? That's about it. Now, if we were using phenolphthalein as our indicator, phenolphthalein would start off pink this time, because we're above 8.2, aren't we? It would start off pink, and then when it got to about 8.2, then it would change color. So with phenolphthalein as our indicator, it would be somewhere around 8.2. There we go. So it's still a good, even though we're going in the opposite direction, phenolphthalein was still good. It's just that we're looking for the color to just disappear now, right? Once again, Congo red would probably be no good, because it would be changing at about pH 3, which would be a little bit too late, and we would have too much of an error here. All right, so we still want the indicator that we pick to change somewhere in this vertical region, either slightly above it or slightly below it, because we want to minimize any error. So there we go. So what does this look like? Well, we know it's a strong base with a strong acid, because our base is the sample. It starts high. Our strong acid is the titrant. That's where we have excess. It ends low. The pH is going to be somewhere around 7, depending on the strength of the acid and base. So there we go. Okay. Well, what's going to happen this time if we have a weak acid with a strong base? So in this case, we could take something like vinegar as a weak acid sample, and it's going to be titrated with a strong base, so say something like sodium hydroxide. So same scenario. We've got this change in pH over time. We've got sodium hydroxide that's being added very, very, very slowly. Now, in this case, we're dealing with something like vinegar, which is a weak acid. The curve is going to start well above 2 this time. Remember, hydrochloric acid started down around this area, because hydrochloric acid is 100% ionized. It's going to have a very low pH because it is a strong acid, again, depending on its concentration. So in this case, we're dealing with vinegar, which is only slightly it has a very small percent reaction, so its pH is going to be relatively higher. So that's one of the telltale signs that we're dealing with a weak acid, is because it's going to start at a much higher pH. And the weaker the acid, the higher it's going to start. So a really weak acid would be up around, pH 6, pH 5, like that. So in this case, we're using vinegar. It starts at around pH 4, again, depending on the concentration that we have. And what we notice is that, once again, there's still enough vinegar in the container to try and withstand the sodium hydroxide. So as the sodium hydroxide is being added, it's being neutralized, it's disappearing, and the vinegar is what's in excess here. Now, what we're noticing is that because the vinegar is a weak acid, it's not able to withstand the sodium hydroxide like hydrochloric did. Hydrochloric acid, as soon as the sodium hydroxide came in, bang, it was neutralized, it's gone, no question. Acetic acid has a little bit more difficulty trying to neutralize the sodium hydroxide. So what we see is the curve is a little more sloped. The hydrochloric acid was almost level, but this guy is a little more sloped. It's up a little higher, and it begins to continue to rise. And as we continue to add the sodium hydroxide, as soon as all of the vinegar is neutralized, again the pH shoots up, because now all the vinegar is gone, and what we're going to have left in this container now is sodium hydroxide. So again, it's going to level off really, really high, because now the sodium hydroxide is what's in excess. All right, and it's going to be up around 12, because that's what's present in, sodium hydroxide is a very, very strong base. Now, one of the things we're looking at here is we might say, at some points of the graph, we say, well, what ions are present? Well, down here, the vinegar is what's in excess, so it's the vinegar that's present. When the vinegar has been neutralized, the hydrogen has been removed. So what's present at this stage is going to be some hydroxide, because the hydroxide's in excess, but also floating around here is now going to be the conjugate base, the CH3COO-, because that's being produced from the ionization of this. So sometimes they ask that question on the exams, what ions are present at what stage. So there we go. Now, the equivalence point is what's important here. Again, the definition of the equivalence point is the midpoint between the vertical region. So when we identify the vertical region of this graph, we notice that that's where equal amounts of acid and base have been mixed. So all of the all of the acetic acid has been neutralized. And what we notice about the pH, because this vertical region was pushed up, because we started at a higher pH, the entire vertical region, the midpoint, is now pushed up. And we've got a much shorter vertical region. So the midpoint is much higher than pH 7. And that's why we used to say the pH at equivalent depends on the strength of the acid and the base. If we have a weak acid, the pH at equivalence now is pushed up. So that's the telltale sign that we're not dealing with a strong acid, is that the equivalence point pH is way up there. Not to mention that we start higher and the curve is more sloped. Okay? So there we go. So pH at equivalence is above pH 7. We start higher. The titration ends at 12 because we're dealing with a strong base. So there we go. Same thing now. We can still figure out the volume at equivalence. Right? We still get that because we drop down right from the equivalence point, and that's our volume. So if we want to do a stoichiometry calculation, that's the volume we would use. And there we go. Okay? So telltale signs here, weak acid, everything is moved up. It starts higher, it's more sloped, and the equivalence point is much higher because the vertical region is now skinnier or narrower, and it's pushed up. Okay, there we go. So here's the idea of indicators. In this case, I have thymo blue that changes at about pH 9. Thymo blue is okay, right? If I drop down the point where it changes from yellow to purple, I'll just mark that with a red line. All right, we're pretty close to the equivalence point. The amount of error, 50 milliliters is the volume here at equivalence. The amount of error is going to be minimal because we're within that vertical region. If we use methyl red, again, methyl red would be okay because methyl red changes well within this, it's going from red to yellow, and it too is changing within the vertical region. So we're in money here, we're good. Either one of these indicators would be suitable. So We're looking at this guy and saying this is a strong acid because it's well below 2. And we're ending with a strong base because we're up above 12. And you notice how the equivalence is very close to pH 7. Okay, there we go. And again, the important thing here is that whatever indicator we choose has to be within the vertical region, either above or below. It doesn't matter, but it has to change color within the vertical region. Here's another graph that shows us a suitable indicator. This was going to be a weak acid because, again, look, we're starting at 3. The curve is sloped up. The midway point is pushed up. The equivalence point is above 7. There we go. Thymal blue, still suitable. In fact, thymal blue was almost dead on, isn't it? Thymal blue for this indicator, for this titration, thymal blue would be almost perfect. Methyl red, however, even though it was suitable in the last experiment, it's no longer suitable because look where it's changing. It's changing right about there. And look at the error associated with this. The amount of error associated with using methyl red is almost 10 milliliters. So any calculations we're going to do here now are going to be way off if we use methyl red as our visual cue for our indicator endpoint. All right. So the indicator endpoint has to be very close to our equivalence point, ideally. Okay, there we go. Okay, here's another one. In this case, we're going the other way. So again, we're dealing with a strong base because it starts above 12. We're ending with a weak acid titrant. So we're probably using something like vinegar or some other weak acid there, benzoic acid or carbonic acid or something like that. So some weak acid here because we're ending really, really, really high. We know we're not strong. So as a result, again, the pH at equivalence is pushed up. Phenolphthalein, perfect. Look, it's changing almost exactly at the end point. Methyl orange. Methyl orange would be absolutely useless because it would never change color. Methyl orange is going to stay yellow for the entire titration event. You're going to do that titration with methyl orange and you're going to say, sir, excuse me, sir, we're not seeing anything over here, right? There's no change. That's because you used the wrong indicator, right? It's not going to go below pH 5 of methyl orange. So there we go. So methyl orange is useless for this, right? Okay, comparison. Just a quick comparison, weak acid, strong base. So weak acid, we're going to start low and end high. The pH is going to be above 7. That's how we identify weak versus strong. Strong acid, strong base. Again, see the difference in the curve. We start low, we end high because both of them are strong. pH is somewhere around 7. Weak acid, strong base. We start high, we start high because it's weak. We end high because it's a strong base. So there we go. So that's the comparison. That's what you need to know. Okay, here's another one where we had a weak base and a strong acid sample. So in this case, because we start with a weak base sample, we're starting well below 12, and you notice how the opposite happens. It's a very greatly sloped here because this is a weak base. And in this case, the equivalence point is way below 7. And we're going to end real low here because we have a strong acid titrant. And if we compare that again with strong and strong, we can see that we're going to start high, very level, shoots down really quickly, and then levels off nice and level because we got a strong base sample and a strong acid titrant. Okay, there we go. So that's the difference. Okay, here's a typical type question. It says, is the titrant an acid or a base? Now the titrant is what we're slowly adding. So right here we have no titrant added, 0 milliliters. And when it's 0 milliliters, we know that the sample is going to be about a pH 2. That's a strong acid. When we have maximum amount of titrant, we know that we're up above 12. So this guy is going to be a base. And not only that, we can make the prediction that it's probably going to be a strong base. Okay? Is the sample acid or base? Well, we just determined that. We said it's going to be an acid because we start with a low pH. This is the volume where we have exactly 0 volume of base added. So this is the entire pH of the unaffected acid. And Okay, this is going to be a weak acid. Sorry about that. Weak acid because of the equivalence point being well above 7. Okay, there we go. Yeah, so the pH is well above 2 there too. All right. How many equivalence points occur? Now this is an important point too. We're going to look at this in the next lesson in a little more detail. But obviously the equivalence point is the vertical region. And in this case, there's going to be one equivalence point, which means there's only going to be one hydrogen transferred. I'm going to write that in. There's a single proton transfer. Only one hydrogen gets transferred. It's a 1-to-1 ratio. And again, I'm going to talk about that in more detail in the next lesson. How many quantitative stoichiometric reactions have occurred? And again, I just did that 1, since we have one equivalent point. There's only one hydrogen being transferred. And it's being transferred right there. That's when it's all gone. Every last one of them have been transferred. So if this was acetic acid would go CH3COOH, and up here it's CH3CO minus, and of course we got excess OH minus. So the reaction that would occur here, of course, would be CH3COOH plus OH minus goes to CH3COO minus plus water. So we get a single proton transfer as the Bronsted-Lowry equation would suggest. There we go, and that's reflected in that single equivalence point. Okay, here's another one. This one says we want to do a titration curve of 0.1 molar hydrofluoric acid, and it's titrated with 0.1 molar sodium hydroxide. Anytime they say it's titrated with, this guy is always the titrant. The first one is generally always the sample. So in this case, hydrofluoric acid, you check your table, it's going to be a weak acid. So the titration curve should start fairly high like that, above 2, and then it's going to shoot up. And as it shoots up, it neutralizes completely, and then obviously we have excess sodium hydroxide. So the graph is going to look something like that. Our pH at equivalence is going to be above 7 because we have a weak acid. Everything is pushed up. There we go. Okay, here's another one. This one says we want to titrate sodium cyanide sample with some standard hydrochloric acid. So what we want to do is we want to look at the idea that, well, what's the species that's present? And in this case, we've got sodium cyanide is ionic, so it's going to produce sodium spectator ions and cyanide. You check your table and you find out that cyanide ions are a weak base. So my sample is a weak base. So when I do my curve, the sample is a weak base, so I'm going to start somewhere below 12, and then it's going to shoot down with a nice steep slope, and then eventually it's going to drop off well below 7, and then it's going to end up being by 2 or lower because it's a strong acid. In actual fact, you could actually calculate the pH here. The pH is going to be the log of that, which is going to be 1. So this guy should end off down around 1. There we go. Okay, so it's a weak base with a strong acid. Okay, and that's titration curves. Make sure you take advantage of our online tutors and all our online material. Check some old public exams, get some questions here that pertain to this. Try them out, check the answers. If you still need some help, then drop me a line in the discussions. All right, see ya.